Charge, either positive or negative, is a fundamental quality that causes objects to experience a force while in an electric field. The net charge of an object is determined by the number of positive and negative charges it has, protons and electrons respectively. Likewise, the electrons of different materials behave differently when the material is in an electric field. Conductors have many mobile electrons that will move in the opposite direction of the electric field. As a result, the internal induced electric field has the same magnitude but opposite direction of the external one, such that the net internal electric field is zero at equilibrium. Insulators, like the plastic tape strips, are materials with few mobile electrons. When in an electric field, the electron clouds of the atoms are distorted such that the induced dipole is in the same direction as the external electric field. However, you can still create a net charge in an insulator by using mechanical motion to remove some electrons. Therefore, the purpose of this lab will first be to charge a piece of tape, second, to find the sign of its charge, and then finally to determine the amount of actual charge lost or gained by the tape. To start, we can create a net charge on the piece of tape by rapidly peeling it off another piece of tape. We can confirm this by seeing that the piece of tape is attracted to my neutrally charged hand, as well as to the neutrally charged textbook. Likewise, when we bring two pieces of tape towards each other, we can see that they are repelled. According to the formula for Coulombic forces of attraction, this is only possible if both pieces of tape are charged and if they have the same sign charge. In order to determine the sign of the charge of the tape, we can observe its interactions with an object that has a known charge. It is known that if you rub a clear plastic object such as a pen through your hair, that object will become negatively charged. Since the pen is attracted to the tape, the two must have opposite charges, hence the tape is positively charged. And we can see this reflected in our calculations. The unit vector shows that the force of the charge will be towards the origin. The pen has a surplus of electrons, while the tape has a deficiency of electrons. At this point, we have established that the tape is charged, as well as what the sign of the tape's charge is, but we also want to know the specific amount of charges that the tape has lost. We can determine this by observing the electrostatic forces generated by the tape in equilibrium. We can create a system with one suspended piece of charged tape, and in the surroundings have an identical piece brought from directly below, such that the original tape is in equilibrium. The original tape, tape B, is not experiencing any acceleration, but we know that it is being acted on by its own weight, as well as the electrostatic force generated by the second tape, tape A. From this we can use Newton's second law to show that the aforementioned forces have the same magnitude. We can also measure the distance between tape A and tape B, just as tape B begins experiencing this force. If we make the assumption that the two pieces have about the same charge, Q, since the identical process was used to charge both, then both would have the same amount of electrons removed, and thus the same net charge, and that all the charge from the tape is coming from a single point, then we can plug all these values into the formula for the force between 2 point charges. Using algebra, we can solve for Q. Using SI units, we get an answer that is in coulombs, but we can convert this to electrons by dividing this number by the charge of an electron. This is the electron deficiency on the tape. If we further assume that the area of an atom is just the length squared, then we can roughly estimate how many atoms are on one piece of tape whose dimensions are also known. We can bring this number and the number of electrons missing together to create a ratio which illustrates what proportion of atoms gave up electrons. I modeled this situation using GlowScript as well. In the constant section of the code, I define the acceleration of the gravity on Earth as well as the Coulombic constant. In the objects part, I create two spheres to represent the point charges of the tape, with tape B at the origin and tape A a little below it. I define the mass as well as the weight in the initial value section, then I represent the weight using an arrow beginning from tape B's center. I had to scale the length of the arrow so that the model was understandable. Likewise, since the weight is the same magnitude as the electrostatic force, I represented this as another arrow of equal magnitude, but in the opposite direction. From there, I define two functions. The first calculates the distance between two three-dimensional vectors. First, this function finds the displacement vector before using the extended Pythagorean theorem to calculate the magnitude or distance. The next function calculates the actual charge given the mass of the tape and the distance of separation. These calculations mirror the physical lab, setting the magnitude of the weight equal to the electrostatic force, then algebraically isolating the charge in the point charge force formula. So at this point, if we look back at our original objectives for this lab, we were able to charge the piece of tape via friction, determine that the tape was positively charged, and ultimately show that the tape had lost around 4 times 10 to the 17th electrons. But in reflecting, we can see that there were some issues regarding our testing methods. It is inaccurate to model all the dipoles on the tape as a single point charge, or to assume the area of the atom is simply its length squared. Additionally, the dimensions of the tape and separation we measured using the ruler likely had large margins of error. With regards to additional questions, if electrons were positively charged and protons negatively charged, by removing electrons from the tape it would become negatively charged. However, the interactions with other objects would remain the same, since the sign of their charges would be flipped too. Additionally, in order to prevent your body or another good conductor from discharging the tape, it is important that we handle the pieces of tape as little as possible in the lab. Thank you very much.